In this module, we'll talk about multi-cloud network architecture. What's the big deal about multi-cloud networking anyway? Well, let's just ask some experts. Let's start with some analysts. Gartner says that as organizations add new applications and scale existing ones into the public cloud, the shortcomings of the native cloud providers become more apparent. Furthermore, they recommend to not forklift traditional networking strategies into the public cloud. Forrester says multi-cloud is hard, but single cloud failures make it necessary for enterprises. As you can see from this infographic, every CSP experiences major outages. And this is not even a comprehensive list. The write-up that has this infographic was written on December 7th, 2021, which was before two more major outages occurred in AWS later that month. We at Aviatrix say you're only in a single cloud until you're multi-cloud. The reality is that the decision to go from a single cloud to a multi-cloud is made in a boardroom. It's made by execs. It's often the result of a merger or an acquisition. And when it happens, you have very little turnaround time to adapt and build in a new cloud. If you're a network engineer, no matter how much of an expert you are in a single cloud or how comfortable you are with it, the decision to move to multiple clouds is usually made by someone else. It's inevitable. It's just a matter of time. Let's talk about the evolution of networking. In the 1990s, Cisco was the dominant player in the data center. Everything was built using physical hardware. You had physical servers, physical routers, physical switches, physical load balancers, physical firewalls, etc. Everything was built on physical hardware. Everything was an integrated stack. What that means is the control plane and the data plane were on the same device. Then, in the mid-2000s, there was an open source protocol developed at Stanford University called OpenFlow. OpenFlow was productized by a company called Nicira with the objective of decoupling or disaggregating the control plane from the data plane. And this is what led to software-defined networking, or SDN. Nicira got acquired by VMware in 2012 and became the NSX division. Just like VMware's ESX platform is a hypervisor of virtual machines, their NSX platform was able to virtualize networks. And that's how private cloud became a thing. Now, in the public cloud, we still have virtual machines running in virtual networks, but the customer has no physical access. In other words, as a customer, you have no access to these virtual machines and virtual networks. So they become a black box to you. The cloud does not provide enterprise-grade networking and security constructs. So as a result, there is a huge architectural gap. If you have no visibility, how are you going to build and how are you going to design? Let's double-click into this idea of reference architectures. When designing a network on-prem, for even the most complex designs, for highly performant, scalable, resilient network infrastructure, network engineers rely heavily on reference architectures. A reference architecture is a blueprint, and it enables us to design in a repeatable fashion. So what you see on the screen on the left is a model from Cisco in the 1990s for building data center networks. It's the classic three-tier model with core, aggregation, and access. And in some places, like campus networks, aggregation is replaced with distribution, but it's the same idea. And on the right side is a CLOS network with a leaf-spine architecture that became popular in the late 2000s. But the important thing to note here is that these are blueprints or building blocks that can be repeated. That is the benefit of a reference architecture. Before we get into defining a cloud network reference architecture, let's talk about the most important part of any cloud network, and that is the transit. And what do we mean by transit? Well, think of it as analogous to the hub in a hub and spoke architecture in an on-prem network. Except that transit in the cloud is responsible for so much more. First and foremost, it is the entity that will allow communication across spokes. And spokes are where your applications are deployed. So you can have a single transit in a region, or you can have multiple transits in a region. Each transit may serve the purpose of different environments, such as production or test. A transit will also allow you to connect to application workloads in different regions. It may be for any reason, such as disaster recovery, performance, or just a different business unit, such as QA. A transit is also how you can service chain advanced services. such as next-generation firewalls, where certain types of traffic can be inspected. A transit is also how you connect to on-prem locations, such as data centers, branches, remote sites, and partners. Aviatrix provides a cloud network reference architecture. This architecture has three pillars: security, cloud networking, and operations. In cloud networking, there are three layers. There is the application layer, where the applications or the workloads reside in VPCs or VNets or VCNs. There is the transit layer, where VPCs, VNets, and VCNs are connected to each other. And there is the access layer, and this is where you have on-prem connectivity. That could be on-prem data centers, branch offices, remote sites, remote users VPNing in, vendors, partners, or IoT. A typical enterprise's journey in the cloud starts with a single cloud in a single region. In this case, it is Azure. The applications of this customer reside in one or more VNets, and when they need to communicate with other apps or workloads, they traverse the transit layer. The architecture allows for on-prem data centers in the access layer to communicate with the app by going across the transit and then to the application. Now let's say the app needs to go out to the internet to get patched, or it needs to connect with a version control system like GitHub. We call this egress to the internet. The reference architecture allows that as well. Now let's say your business is growing. You're growing from one region to multiple regions. The transit of this cloud architecture allows connectivity across regions to carry traffic between the workloads, so your application can work seamlessly even after growing to multiple regions. For security and compliance reasons, you'll want to make sure your important applications are protected by next-generation firewalls. Maybe it's for revenue-generating environments. You'll want traffic to be inspected by these firewalls, and you'll want to apply a policy that will steer only certain traffic to those firewalls so that you're not wasting valuable resources on the firewalls. What about if your branch office is connected to one region, but it needs to access resources in another region? Well, this architecture allows that as well. So the branch office is connected to its home region, and from there it hops on to the transit layer, and then to the application in the other region. And this applies to remote users as well. Remote users could be anywhere in the world. They could be on the road traveling. They need fast, seamless connectivity to their applications without needing to worry about their certificates and profiles needing to be changed every time they travel. Security must be provided at every layer. And by that, we mean security by means of inspection, security by means of segmentation and isolation, security by means of end-to-end encryption, which is available by default. This architecture provides all of that. Now, this is all day 0 and day 1, but what about the day 2 lifecycle? Well, the architecture also takes care of that. In other words, it is built to operationalize the infrastructure. It is built with operations teams in mind. It has all the troubleshooting and visibility tools your operations teams used in on-prem networks. This data plane in the cloud belongs to you, and therefore, the operations teams must be enabled to perform their roles in the cloud. So this is the reference architecture for a single cloud enterprise. Now what happens when they go to multiple clouds? The architecture doesn't change at all. It doesn't matter if you're now in AWS or GCP or OCI or Alibaba Cloud. The architecture is the same. It repeats itself. That is the beauty of this architecture. And it's called simply Multi-Cloud Network Architecture, or MCNA. The approach for building in one cloud is repeated when building in multiple clouds. You don't need to know all the subtleties and nuances about the underlying constructs. The Aviatrix multi-cloud network architecture will abstract them from you. Aviatrix will smoothen those bumps so that you can operationalize everything. And you can do that from the UI of the Aviatrix platform, as well as via API, as well as via the Aviatrix Terraform provider. Now let's put this together in a more complex real-world scenario and see how MCNA can be applied. Let's start by focusing on the left side of the diagram, where we have AWS. In the application layer, in the top left, we see VPCs with application workloads. And in each VPC, we see a red circle with arrows pointing towards each other. Those VPCs are called spoke VPCs, and those circles are called Aviatrix spoke gateways. Those spoke gateways are connected to Aviatrix transit gateways, which are in the transit layer. So Edge VPC is a transit VPC in the transit layer. Remember, it is the transit layer that connects the workloads in the application layer. Now, in that Edge VPC or transit VPC, you also see a couple of firewalls for inspecting certain traffic that we define in a policy-driven manner. What about data centers and partners and remote sites that are on-prem? They are in the access layer, and they will also connect to the transit layer. They may come in via private circuit like Direct Connect or via IPsec VPN. Now let's look at the middle of this diagram where we have Azure. The Azure architecture is identical. You have applications or workloads in the application layer in spoke VNets. You have Aviatrix gateways in those spoke VNets. You have transit gateways in transit VNets, which are in the transit layer. The spoke gateways and the transit gateways are connected, and all these connections are encrypted. We also have private circuit connectivity in the bottom center of the screen, this time with Azure Express Route. And if you use an Aviatrix Secure Edge gateway on-prem, then the connectivity from the remote site to cloud is also encrypted. So you get end-to-end encryption. You can connect the AWS transit with the Azure transit, and that's called transit peering. GCP is no different. You can also peer with GCP transit to get full connectivity among all clouds. And by the way, this entire cloud infrastructure can be programmatically built via API and via the Aviatrix Terraform provider. Not only can it be built, but the entire lifecycle can be automated via Terraform. All these features shown on the screen can be used with the Aviatrix Multi-Cloud Network Architecture, or MCNA. In the next module, we'll discuss some of the Aviatrix platform features.